Problem scenario. Imagine you are the lead engineer of a popular e-commerce platform and your team is tasked with optimizing the platform's recommendation system. The recommendation system uses a priority queue to manage and process product recommendations for each and every user based on their browsing history, purchase behaviors, and preferences as well. So, during peak shopping seasons such as Black Friday or Cyber Monday, the platform experiences a significant increase in user activity, leading to a surge in recommendation requests. To ensure that users receive timely and relevant recommendations, you decide to implement a priority queue system using Fibonacci heaps. However, you need to devise a strategy for managing decrease key and delete operations efficiently to handle the increased workload effectively. So, here is the scenario. During the Black Friday, the e-commerce platform receives 10,000 recommendation requests per minute, each assigned a priority value based on various factors such as user preferences and purchase history. The recommendation requests are processed using a priority queue implementation with Fibonacci heaps. Lower priority values indicate higher relevance. As new recommendation requests arrive, the priority queue dynamically adjusts to prioritize the most relevant recommendations for each user. To maintain efficiency, the system frequently updates the priority of recommendation requests based on real-time factors such as product availability and user engagement. However, as users interact with the platform, such as browsing or purchasing items, the system must efficiently manage decrease key and delete operations to update recommended priorities and remove outdated recommendations. Additionally, the system must handle sudden changes in workload gracefully, adjusting the heap structure and optimizing decrease key and delete operations to minimize processing delays and maximize the accuracy of recommendations. So, your task is to devise a strategy for managing decrease key and delete operations in the priority queue system using Fibonacci heaps, ensuring optimal performance and responsiveness even during peak user activity periods. So, here is the solution. To address the surge in recommendation requests effectively, let's consider the following numerical example. So, during Black Friday, if the platform receives 10,000 recommendation requests per minute, we can expect approximately 166 recommendation requests per second. Let's assume each recommendation request requires an average of zero point 0.5 seconds to process, including updating priorities and adjusting the heap structure. So, with Fibonacci heaps, the decrease key operation typically takes big O of one-time complexity, allowing us to efficiently adjust the priorities of existing recommendation requests. For delete operations, we can adopt strategies such as lazy deletion or delayed consolidation to minimize overhead. Let's calculate the total processing time requiring for handling recommendation requests during peak activity periods to determine the system's responsiveness. Total processing time equals the number of recommendation requests per second multiplied by average processing time per request. Total processing time equals to 166 multiplied by 0.5. So at last, total processing time is approximately 83 seconds. By efficiently managing decrease key and delete operations in the priority queue system using Fibonacci heaps, we can ensure optimal performance and responsiveness even during peak user periods, minimizing processing delays and maximizing the accuracy of recommendations.